Okay, so now we have Pioneer Borges, who's going to tell us all about Falconer type results for finite graphs with multiple pins. So whenever you're ready, please do begin.
Thank you. Thank you, Will, for the invitation. Thank you, the organizers, for the organizing this conference. And I guess thank you all for being here on a Saturday. Yes, so this is not on archive yet. It's probably going to be there this week. And it's a joint work with Foster, O. Paulson, and Romero Acosta. Um, I guess our starting point is the Falconer distance problem. So here we have like this compact set in RD, and we're collecting all the distances that are realized by pairs of points in E. And we also have a version of this where you're only looking to distances realized from a certain fixed point in E. So this is the pin distance set of E at this location Y. Um, in 85, Falconer conjectured that as long as you ask enough on the Hausdorff dimension of E, there should be a lot of distances attained in E in a positive measure sense. So this was, and the right assumption, the conjecture assumption is that the dimension of E is strictly larger than D over 2. Half of the ambient dimension should be enough for this set having positive measure. And this is only in D at least 2, because in the real line, this question breaks down, doesn't make sense. Now, the way that the question is stated right here, this was not proved in any dimension, so this is an open conjecture, but people have been getting closer and closer to this threshold, D over 2. So far, if you ask a little bit more on the dimension, you can guarantee this. Originally, when Falconer posed this conjecture, he proved that if you ask an extra half on the dimension, then sure, you have this positive measure property of the distance set. And also, he argued that one cannot expect something better than D over 2. So he showed examples of sets that have dimensions strictly larger than D over 2, for which the distance set has measure 0. So, and there has been a lot of activity on the Falconer distance problem, and I'm going to mention the state of art. So in 2020, Goof, Yosevich, O, and Wang, they obtained the threshold 5 quarters in the plane. So as long as you have a set of dimension larger than 5 quarters, which if you think about is an extra quarter on the Falconer conjecture, then the distance set has positive measure, and that's true even in a pin sense. So you can find the location you need where you collect all the distance from there. This is going to produce positive measure. Now, in dimension at least 3, the best threshold is asking a little bit less than an extra quarter, and this is a result of Du, O, Ring, and Jung from 2023. So you can see this is like recently new, like 2020, 2023, and there's a lot of activity involving Falconer distance problem. Um, Another thing is when it comes to positive measure, if you check the best thresholds, even though in principle proving a pin result would be harder, the thresholds match. So the best that people can do for pinned and unpinned is the same when it comes to positive measure. Um, Now I want to talk a little bit about another question that you can ask. So if I give you a compact set and you are looking at like how big the distance set could be, maybe you want more than just having positive measure, and maybe you would want to have some interval inside the distance set. Um, so there's a result of 99 from Attila Jolin that says that if you're asking for an extra half on the Falconer conjecture, so D plus 1 over 2, any set with dimension larger than that should have an interval in the distance set. And then in 2000, 1 year later, Perschlag also had in one of their papers a result about a pin version of this, where if you want to find a location in E so that the pin distance set has an empty interior, then you can do that, but asking a little bit more from the threshold. So here there is a mismatch from what you need for unpinned non-empty interior and pin non-empty interior. So a big gap of 1/2. Now, if you think about this threshold, it's only helpful in the at least 3, because if you plug the equals 2, you're getting a trivial, like a vacuous result. There is no set in the plane with dimension larger than 2. Great. Perschlag only says stuff in dimension at least 3. And one might be interested in the result in the plane. If you are interested in some specific cases like products of Cantor sets and things like that, there are some results in the literature, especially I want to mention Shimon and Taylor in 2020, where they do prove like pin on empty interior of the distance set, as long as you are keeping for your product or Cantor sets, you're talking about Cantor set where you kept enough at each stage of the construction. Now the question remains like, what can you find in the plane for pin on empty interior? And we studied this question, and now there's something else that should be said in the plane. If you have a compact set in the plane with dimension larger than 7/4, which is like 1.75, or maybe you are in R3 and you have like dimension of V larger than 2.4, then you can find non-empty interior for the pin distance set, pin the sum location of V. I guess now the thresholds you can illustrate in a line right here. Like, so in the plane, it's interesting that the jumps are always like 1/4. So Falconer conjecture is here. Like anything with dimension larger than 1 should be fine for positive measure. The current best threshold is 5/4, so you're 1/4 away. Then if you ask for an extra half, you have non-empty interior. If you have an extra half on the dimension, you can get P non-empty interior, and then Perschlat was not saying anything. So there's some open questions here, like trying to bring these thresholds closer together, right? Maybe all of them potentially could be coinciding here at the Falconer threshold, maybe not. Like it's not very clear that the non-empty interior question should match the positive measure question. So that's an interesting question. And then there's also like some picture that you could draw here in dimension 3 where the Falconer conjecture is halfway and there are current best results for positive measure. And then you see that there's some gaps between pinned and unpinned non-empty interior. So these are only a few of the questions that you can ask of a Falconer flavor, like positive measure, non-empty interior, pinned, unpinned. You could also maybe potentially be interested in dimension estimates. People have done things like that. And there are other ways in which you could generalize these questions. So here's one thing that one might be interested in. Maybe you have a graph structure, like say a chain, right? So here I'm looking at a 4 chain, has 5 vertices, 4 edges. And what I want to think of is like, when I give you a compact set, I kind of want to sample those vertices in E and keep track of a vector of distances that would be showing up by that realization of this graph in E, right? So for this graph, we could then, like, given a set E, generate like vectors in R4 and ask questions about like positive measure in R4, for example, right? So what is the distance set here? It's what I said, like you're going to be sampling the points. So here you're going to need to sample 5 points, x1, x2, x3, x4, x5 in E. And then for whatever of those realizations, you're keeping track of 4 Euclidean distances, sort of what we would see for the lengths showing up right here. And of course, you could maybe pin somewhere, right? So here I gave the example, or you maybe would pin in the first vertex and then keep track of all the 4 chains with pin in view 1. You could also do this for more other graphs, like another example. Say you have this tree and you decided that you want this pin, the pin to be in this location in magenta, V naught. And then the distance set associated to this tree would be sampling at every realization. I would only be sampling 5 points and keeping track of these distances. And if I'm pinning, then I don't need to sample, so I'm only sampling x1, x2, x3, x4, and varying over all the distance that I realize that. So I'm sort of fixing V naught should be x naught. And the kind of question that you can ask for those 2 guys, like maybe you want to ask a question of, can you find a location x naught for which this tree distance set has positive measure in R4, for example. Here's some things that have been studied in the Matilda-Jolin sense, so non-empty interior sense. So if you, this is a result of Bennett, Yosevich, and Taylor from 2016. If you know that your set has mentioned at least D plus 1/2, and you're keeping track of all the chains realized in E, this set has an empty interior in RK. So this kind of question right here, if I was sampling these points in a set of dimension larger than d+1/2, I would find an empty set in R4 for the distances. And there is also a version of this for trees, which is a paper from 2018 of Yosevich-Taylor, where they even stated this in a constant gap sense. So whenever you have a set of that dimension threshold, you can find trees of constant gap T for whatever tree structure you're interested in. I guess here maybe we should notice this is unpinned. Those results are unpinned, and that's kind of important. There is also the question of positive measures. So this is about an empty interior, and the threshold d+1/2 matches the one that one knows for the distance problem, the Falconer one. Now here you could also be interested in positive measure, right? So we have the tree, we have the vertices, and we picked the vertex that you want to pin, and the distance side here is defined as in the picture that I had before, where you're keeping track of all the edge lengths that show up for the tree. Owen Taylor, they found something about this. So if you are under the same dimensional assumptions of the Falconer problem, so 5/4 in the plane or the new threshold in the at least 3, you can use their method to get pin positive measure of any tree you want with the location of the pin chosen. So here is positive measure of trees with pin picked to be somewhere along the tree, and you can do this with the same thresholds as Falconer. I'll go back to that in a second. So one of the motivating questions that we have right here is like, so far we only talked about one pin, but when you start having more complicated graph structures, you might be interested in pinning multiple locations. And the more pins you add, maybe like you could think that it's more rigid, like it gets harder to make sure that this is going to be a big set in the corresponding RK. But it's not very clear at first how the location or number of pins would affect the result that you get. So here's a picture, maybe like I want to place like 4 or 5 different pins in magenta here for this tree, and I want to just sample V6, V7, V8 in E. When do I get a positive measure? Okay, now another thing that one could do is like you might start wanting to see things that look like loops, right? So far I've talked about chains, trees, like there is no loop showing up there. The simplest structure where you start seeing the loop is a triangle, right? And maybe I want to pin here, V1. The distance set that you get is just keep track of those 3 edge lengths every time that you sample the vertices in E. And there is also a pin counterpart of that. I guess like the first paper that I know of that it was studying this kind of configuration in the continuous setting was this paper of Greenleaf-Yosevich, 2011, I think, where they showed that under the threshold 7/4, you have a positive measure in R3 for this unpinned triangle set. So this was the first result, but more recent result from 2025, and this is not the only activity relating to triangles. Triangles have a very rich literature, but the paper that's very relevant for this work is this result in 2025, where they brought down the threshold to d+2/2, even for a pinned triangle situation. So this is helpful as long as you are in dimension at least 3, threshold d+2/2, and it's pinned. Now, there is also like a gap between pin and unpinned results if you are in low dimensions. So in dimension 2 and 3, if you don't care for the pin somewhere, there is a better threshold in a paper 2015. And this is like a gap even in the positive measure sense. So there's like some interesting open questions in trying to close gaps between pinned and unpinned results, even in the triangle setting. Another structure that might be interesting is like maybe you, instead of just having a 3 cycle, you want to do like K cycle, like a generalization of a triangle, and sample your vertices in E, keep track of the distance set. There has been some activity related to cycles in this paper of Greenleaf, Yosevich, and Salmonek. Okay, so this is a paper from 2017, and they were only looking at even cycles. So this, for example, does not include triangles. And it's And then what they're doing is, if they have dimension larger than d plus 3/2, you can find even cycles realized in E that have constant gap, where the constant gap can be anywhere in an interval. So I guess this is some sort of other manifestation of non-empty interior kind of result, where they're even saying something that feels slightly stronger, where you can even realize this structure with all the xylems being the same. The constant gap feels a bit more restrictive than an empty interior. But they're not really comparable if you think about that for a bit. There's also a new result in dimension 3 by Jozevic, Magyar, McDonald from last year, where they take care of 4 necklaces in R3 under a threshold that looks a bit weird, but it's 2.887, around that. So here, this previous result didn't say anything about D equals 3 actually, and now there's something in dimension 3. I guess another thing that we are trying to investigate here is, like, for example, for necklaces, what if you have pins, right? And we're not going to place pins in consecutive locations because you don't want to pin a full edge. If you pin a full edge, then you might as well just discard that edge. It's not varying. It's not going to produce positive measure. So you might see here, I was careful enough to place the pins in a way that I'm not fixing an edge. And when does this have, when is this producing positive measure when sampling the unpinned vertices in E and finding good locations to place the magenta vertices in E? Okay, but this is a general question. So if you have your favorite graph, you know the vertices, you know the edges, and you fix the locations that you want for the pins, call that set P. Make sure that you're not pinning consecutive locations. It makes sense to define a distance set associated to that. So the notation that I'm going to use right here carries the P just to remind ourselves of what are the vertices that we're pinning in this graph G. And say we're pinning those vertices at locations x1, x2, xm. The rest is essentially just for every edge, we keep track of the distance for a sampling of the unpinned vertices in E. Whatever you have, this is going to be a subset of R to the number of edges of your graph. And it does make sense to ask, what are the thresholds that I need on the Hausdorff dimension of V so that there are locations to pick those spins so that the corresponding distance set has positive measure. So this would be a generalization of all the questions, all the pin questions that we've seen so far for the Falconer distance problem, the chains, the trees, the cycles, triangles, and simplices, and things like that. And it's going to be interesting and not obvious to us to understand how does the number of pins, the location of the pins is going to affect this threshold. Okay, so I guess one, if you're familiar with a little bit of graph theory, you might have heard about the notion of K-degeneracy. We need a generalization of that notion that we call K-admissibility. And it has to be of how hard is to construct your graph if you have simple structures that resemble tree-like graphs. But let's slow down here a little bit. If I give you a pin graph, so the choice of pin is fixed, we're gonna say that the graph is K-admissible if it can be constructed in a few steps. You need to start with the pin vertices. Those are your starting point. And then at each step, you're gonna add an unpinned vertices in any edge that has with previously added vertices. So here we add the m+1, some vertex that's not pinned, and we, at that stage, add any edge connecting to the pin vertices. And we keep doing this. So in the second step, you're going to pick another vertex that was not added yet, and you're going to add any edge of that vertex with previously added vertices. And if you want your graph to be K-admissible, you would want that in every stage of this process, you're not adding more than K edges at once. So the back degree of any unpinned vertex in this process is not more than k. If you can do this and add all the unpinned vertices with never using more than back degree k, then your graph is k-admissible. So maybe it might be better to think about like what is this in some specific examples. So when it comes to chains, if all you have is a pin somewhere, you can think that you would be able to delete like segments one-on-ones. And at the end of the day, you can construct a one-pin chain with just adding unpinned vertices with back degree 1 at a time. So that's easy. Now, if you start adding more pins in a chain, so actually it doesn't matter how many you add, no consecutive, you're always going to need two admissible situation. So it might be possible to add unpinned vertices with back degree 1, but eventually you're going to be forced to add one vertex with back degree 2. Here's an example that might about trees, right? So here we have 3 unpinned vertices, and you could add maybe like a V6 first, and you see that would have like back degree 3 with the pin vertices. And then you add V7, which would have like back degree 2. Then you add V8 with back degree 2. So this graph is 3 admissible. It's 3 admissible because in also 3 is the optimal admissibility. You cannot do this with 2. Now necklaces, it doesn't matter where you place the pins, they're always 2 admissible, right? For example, in here, you could see that, oh, I can add this one with just back degree 2. And in this part of the graph, when you add V6, it's back degree 1, but when you add V7, it's just like back degree 2 as well. It doesn't matter which cycle structure you have, what pin cycle structure you have, it's always going to be possible to do this with back degree 2, construction with back degree 2. And then here, like a little structure that I've seen also showing up in some other works. It's called the double banana. So you see like the banana in the right, the banana in the left, and then here it picks the pin to be a V1. If you play with this graph, you're going to see that the admissibility of it is 4. So however you decide to do this, like the best way to do it is going to force you eventually to add a vertex with back degree 4. Honestly, to decide on the admissibility of a graph, it's actually better to think about deleting vertices. And you could start deleting vertex that have the smallest possible back degree, and then you just keep track of like what was the largest back degree that you saw along the way, and that's like the optimal admissibility of the graph. And you can never delete pin vertices, essentially. So this like generalizes an algorithm of, in the case of k-degeneracy. The key thing is it's actually not hard to decide on the k-admissibility of a graph. So it doesn't matter how complicated is my pin graph. Deciding on what the k-admissibility is something that we can do in like finally many steps. And it's not too many. It's like around the number of edges or something, a number of vertices. So what do we have? So one of the main theorems that we found has to be with this notion of k-admissibility. So if you have the graph and you have the locations that you want to pin in the set P, if the spin graph turns out to be k-admissible, then whenever you have a compact set with dimension larger than d plus k over 2, it's gonna be possible to find a positive measure result for associated distance set to that pin graph, where the pins are chosen somewhere in E. And now, like this k-admissibility has to be with how you would build this graph. So this is a picture of what we call a 7 star. So here, a pin 7 star has pins in all the leaves, and then it's a pin in the center. This is if we stare at this for a second, we're going to see there's only one unpinned vertex to be added. This is the simplest possible example of 7 admissible graph. Those are sort of building blocks that if you start like gluing together stars, you can get you whatever graph you want. So the idea is that if you have thresholds that work for k stars, you want to find ways of gluing this together and get you any graph. In a k-admissible graph, you could think of as a graph that you can do this by never using stars that are larger than size k. So this threshold d plus k over 2 right here has to be with like the currently best known threshold with for k stars, which was obtained in this result in this paper of Yosevich, Fon, and Shane in 2025. Also, it's interesting that this structural theorem right here, it could take in any threshold that you can cook up for stars, and immediately you upgrade thresholds for many different types of graphs. So it gives a lot of reasons for us to try and improve structures like that are pinned at the leaves and have an unpinned vertex in the center and like those K stars. What is the best threshold that you can cook up? This threshold d plus k over 2 right here, it's probably not optimal. Actually, we're currently improving this. I conjecture that probably it's more likely to be like k minus 1 instead of k right here, as long as you have k strictly larger than d. But this is the best known at the moment, d plus k over 2. Okay, so now if you take that structural theorem and go back to some of the graphs that one has, you could like check what thresholds one can get for positive measures. So for triangles, the admissibility is 2. You would add one vertex with back degree 1, one vertex with back degree 2. That means threshold d plus 2 over 2 is possible. With simplices that you want to realize in a fractal set, the admissibility is, well, for example, in this picture, every vertex has degree 4. The admissibility of this is going to be 4. So the threshold is d plus 4 over 2. And this was something covered by Yosevich on Shane. Actually, that was one of the main things that they were studying, simplices. And now, like, we put this in a very general framework where that's just a particular case. For cycles, as I mentioned before, like it doesn't matter where you place the non-consecutive pins in your cycle, you're always going to have two admissibility. So the threshold d plus 2 over 2 is always going to work for positive measure of the corresponding distance set. Now you can start cooking up different things. Like, for example, here I have the same graph, but different choices of pins in this graph. Some sort of chain of triangles. In the left-hand side and in the middle, both these graphs are going to end up having admissibility 3. But this one right here in the right has a better admissibility, has admissibility number 2. So this is going to both of these are going to produce like results with this threshold, while this is going to have a smaller threshold. But it's interesting because these guys have the same number of pins, but that's not enough to decide on the admissibility number, right? So the way that they are placed matters. And here you do have more pins in the left than here, and they end up having the same admissibility number. Here, another example, like if you want to do things with like fans, which is like some sort of chains of triangles attached by edges and not by vertices, like this also ends up having admissibility too. So if all you're collecting is edge lengths, realizing E, the threshold is going to end up being d plus 2 over 2. And the distance set that you're thinking about here is a subset of R13. So it has the number of edges in this graph structure. Now, I guess like even looking at this question, maybe you would wonder like why, maybe like you don't care for what lengths you're realizing by sampling the vertices in E. Maybe it would be more interesting question for us to think about areas. Well, both of them are relevant. So let's move to that. Like, what if you're interested in keeping track of areas realized by graph structures that have cycles? Okay, so here's the notation that we're going to use for the area of a triangle with vertices at those points. And we could potentially pin two of the vertices. For example, here we're using this notation for the area set realized in E when x1 and x2 are fixed, and we're only varying x3. There is a result from 2025. One of the things that they proved in that paper was the following. So this is in the plane, and you have a set that has dimension strictly larger than 1. Then there's already a lot of areas. That's a very good threshold, by the way, dimension larger than 1. It's optimal so for this problem. And then you can find locations to actually double pin your triangles, and you just vary the third pin, and that's enough to produce positive measure of areas that you see just by varying the third pin. We revisit this problem also in this original paper, they one thing that we needed and it was not here was like the abundance of x1, x2. I didn't emphasize this enough before, but when you want to like start building things, it out of K-stars, for example, even before, it's important to know that there is lots of places that you could do that, like that you could place the pins. There's abundance of good pins. So we revisit this. We found like abundance of places to do this double pinning, and as an application, for example, you could take care of chains of triangles in the plane. So with the same threshold as before, as they had, now you can even get like vector area vectors realized in E with, like, say, the pin here. By area vector here, I mean you sample those vertices, you keep track of this area, you keep track of this area, you keep track of this area, and you're varying all those guys in E. And this is picked to be somewhere x1. And the notation here just means a triangle chain of length 3. And this is notation of area distance set. It matters if they're sharing like edges or if they're sharing vertices. So in the plane, this makes sense in general. So if you have this graph structure of two triangles sharing like this edge, here, because I placed the pins in V1, V2, I would just be varying x3, x4 and keeping track of this area and this area. I get a certain area set associated to this edge pin structure. So in the plane, actually, so far, we cannot do this with the same threshold 1. We found, though, like that threshold 3/2 works. And then you can get positive measure in R2 for this vector areas that we realized in chains of triangles sharing edge. Both these results are in the plane, and one of the interesting, there's a dichotomy here when dealing with areas in our paper, that there is very different methods in the plane and in dimension at least 3. In the plane, we're using like sort of projection-like estimates, so radial and orthogonal projection exceptional estimates, if this means anything to you. And while like in dimension larger or equal than 3, we still like sort of transfer some sort of information from stars to areas, like two stars to areas. So in dimension at least 3, what we find is the following. So if you have a set of dimension this is supposed to be strictly larger than D plus 2/2, then there's lots of areas. And you can even double pin your triangle and still find that. Now, if you're thinking of a fan, but now you're placing all the pins here outside, so there's many pins, so 7 pins right here, for example. This kind of, and you're keeping track of areas, 7 areas, but only vary this guy. You can also find results there, like in the threshold it's much worse depending on the number of pins you put in here. Like the more pins you have, the larger this becomes. So here for 7 pins, this is D plus 7/2. So I even had shown you before the pin with the pin here. So placing the one pin here is much better than placing multiple pins here, if you're keeping track of the areas. And there's another example that we have where like you can actually start mixing up sharing edges and vertices, and that's still like you can still apply the methods that we have. With the threshold d plus 2 over 2 that one has for chains of triangles, you could deal with things like that. So sharing both edges and triangles here, we can even double pin this edge. And then you can track up this area, and this area for whatever realization you have of those guys in E. I think I changed the label of the vertices. So here, if you're looking at this picture, you would have to do x3, x1, x, oh no, that's correct. Vary x1, x2, x3, x4. Okay, so, but before we go there, so I guess one could think of as this moving to an area discussion as trying to bring the discussion from a graph discussion to an hypergraph structure, right? Because now every time you compute an area, you have a function of that is takes as input like three different numbers, like three different vectors. While before, like when you're just doing distances, you have like you're just computing the distance between 2 points at a time. So this is gonna be so actually this is gonna be two papers. The first paper would just take care of the distances, and then the second paper we try and move the discussion to hypergraph, where we also investigate volumes and other quantities that take in as input multiple vertices instead of two. Okay, so now I want to give you a summary of some of the main ideas that this paper brings. So first thing is that when you talk about k-admissible graphs, like this unifies the discussion of many sort of generalizations of the Falcon distance problem that people have investigated. This second thing is that the threshold that we have so far, the d plus k over 2, does like work for any k-admissible graph, and this is an non-trivial threshold whenever you have dimension large enough. Deciding on the k-admissibility is not a hard thing. In the past, like some of the results that you might find for some of the graphs like require some intricate computations, but here like deciding on the k-admissibility is something that you can do by deleting vertices and deciding like what kind of stars you're using along the way. So that gives you, in particular, you could even always use, if you wish, the max vertex degree as like a trivial, like an immediate threshold that you get, like d plus max degree divided by 2. And if you check the admissibility, you have the d plus k over 2. But when one can even potentially improve that threshold just by looking at what can you say better for k stars. And whenever you improve the threshold for k stars, you get improvements for many different kinds of graphs. And then the last thing is the moment you start allowing loops, and you can also be interested in areas, volumes, and other structures that might be coming from some sort of hypergraph vision that you have for your discussion. And I think that's it. I even finished early. That's good. Thank you.
Okay, thank you for the lovely talk. Let's thank the speaker. I think there's like clapping emojis you can do, but I can't find them. Are there any questions for Tanara?